Hi, I'm Elad. I'm the founder and CEO of NextSilicon. I have an unusual hobby. I collect old computers. I've always believed that if we want to invent the future of computing, we have to understand its past. Today I want to share what we are doing at NextSilicon. How we take on some massive challenges, so massive that nobody else has dared to try to solve them. And the reason we can, it's because we understand the history of computing. I'm a software engineer. Back in 2009, I founded Integrity Project, a company focused on solving low-level software challenges in high-performance computing, networking, and more. The company later got acquired by Mellanox. That's where I first came face-to-face with the challenges of the high-performance computing world, the exploding demand of compute power, and just how complex GPU integration really is. For decades, I've watched the world's most sophisticated supercomputing customers like Oak Ridge and Sandia National Laboratory. They struggle with rigid CPU and GPU architecture. This has become a multi-$100 billion problem. Massive code rewrites, nightmare porting scenarios, skyrocketing energy cost, and smaller performance gain. These have all become the norm. I saw this a decade ago, long before the broader tech industry even recognized the problem. Let me tell you how we are solving that problem. We have invented a radical new compute architecture, purpose-built and original. It combines software intelligence and hardware flexibility in a completely new way. Unlike others who are just focused on solving the hardware problem, we take a complete system approach. For the first time, we are bringing together hardware and software, a data flow processor with a smart software algorithm, a new compute platform for the next-gen AI and HPC. Our data flow allows your data to drive your application and optimize your software, not the other way around. We have seen that for compute-intensive applications. A small portion of the code, a tiny bit, runs the majority of the time. We have decided to take it to our advantage. Instead of running every piece of code, every instruction the same way, we thought, let's focus on what matters. We developed a smart software algorithm that continuously monitors your application. It identifies precisely which code path ran the most, and it reconfigures the hardware on the chip to accelerate exactly those code paths. And we do this all at runtime in nanoseconds. The result? Efficient performance at scale for the most critical workloads, freeing you to focus on innovation, not overhead. I know what you're thinking. Reconfiguring silicon on the fly, at nanosecond speed must be incredibly hard. So complex that it sounds impossible. That is why no one else has even attempted this before. Two different disciplines working together, hardware and software. Our vision isn't just big, it's revolutionary. NextSilicon is redefining computing by creating an entirely new generation of compute infrastructure. Our technology seamlessly runs CPU and GPU code, supercomputing tasks, HPC workloads, and advanced AI machine learning models, all effortlessly, out of the box, and as a drop-in replacement. This means no vendor lock-in. Our customers can spend more time doing what they love instead of code rewrites and porting. At NextSilicon, we are reimagining what computing can be, where hardware finally bends to the needs of software, not the other way around. Just as GPUs once displaced CPUs, our architecture is poised to redefine compute all over again. Today, I will show you exactly why. 8 years ago, I explained my new startup idea to a relative, describing my plan to accelerate computation. My laptop already works fine. Why do we need faster computers? I then realized something, that most people don't even notice the revolution that is happening right before their eyes. Humankind built computers, massive HPC centers, to solve the world's greatest mysteries. Today, computing powers breakthroughs in science and healthcare. At Lawrence Livermore National Labs, scientists work with cutting-edge supercomputers. They have managed to achieve net positive nuclear fusion energy, a key milestone that brings us closer to a future of limitless clean energy. At CERN's Large Hadron Collider, a supercomputer analyzes petabytes of data, uncovering discoveries in particle physics like the Higgs boson. Companies like GE use software to design and simulate jet engines. They make changes in a virtual world, saving resources and speeding up innovation. And in medicine, supercomputing is key in accelerating drug discovery and vaccine development long before physical trials. Computing also predicts disasters like severe weather, helping prevent tragedies. Supercomputing saves both dollars and human lives. Even if you haven't heard of HPC, you have probably heard of AI like ChatGPT, Gemini, and many more. The math that powers AI factories and HPC research is the same. They are all made possible today by very powerful computers. Looking back, it is interesting that AI has taken this long to gain traction. We already knew how to build AI neural network back in the 70s, but we couldn't bring them into commercial use until 2012. It took a competition called ImageNet that introduced a deep learning model named AlexNet to change everything. It was the first neural network to classify images, telling the difference between a cat and a dog or a hot dog, or between a chihuahua and a muffin, with near human accuracy. Here is why AI struggled before. Running just one image through AlexNet required 8 billion calculations, 8 billion floating point operations. Something that would have taken a 70s computer 90 minutes to compute. We didn't lack the science, we lacked the compute power to support this new innovation. So how can you run science code and AI? Let me walk you through Computing 101. CPUs and GPUs are based on an 80-year-old architecture. Their goal is to optimize every single instruction the same way. The first microprocessor, the Intel 4004, was launched back in 1972. It had only 2,300 transistors. Since then, we enjoyed Moore's law scaling, and CPUs became so sophisticated that they are now consume nearly 180 billion transistors. However, these improvements in sheer manufacturing peaked in the early 2000s. For many years, CPUs were the main choice. CPUs work by executing one instruction, then the next instruction, and then the next. This is called serial processing. You can program them easily using common languages like C, C++, and Python. They are perfect for running operating systems and everyday software. But CPUs are designed for a specific purpose. They focus on doing tasks quickly, not on doing many tasks at the same time. Also, here is a surprising fact. In modern CPU core, only about 2% actually does the math and calculation. The other 98% is used for managing and organizing the work. This means customers pay for chips where most of the hardware doesn't solve their actual problems. Instead, most of the chip space goes to complex control systems and overhead. CPUs are focused on completing a single sequential stream of instructions in the shortest possible time. This approach worked well for simple tasks that happen one step at a time, but it reached its limits. By the mid-2000s, this pushed the industry to try new approaches, which led to using GPUs for tasks that need to do many calculations at the same time, also known as parallel processing. GPUs were first created for graphics processing. They used many smaller cores to do many things at once, all in parallel. This started with making video games and computer graphics run smoothly. But engineers quickly discovered something important. The GPU design was incredibly powerful for many other types of work. Think of it this way. A CPU is like having one very skilled worker who can handle complex tasks quickly. A GPU is like having hundreds of workers who each do simpler tasks, but together accomplish much more. The real breakthrough moment for GPUs came with the rise of AI and machine learning. For these workloads, GPUs were not just slightly better than CPUs. They offered an order of magnitude in performance improvement. This massive advantage transformed the GPU from a niche graphics processor into GPGPU, a general-purpose GPU. A chip that could accelerate many different types of computing tasks, not just graphics. Funny enough, GPGPU, general-purpose GPU, isn't as general as a CPU. It's not a one-size-fits-all. GPUs have three key challenges: software, resource trade-off, and power. Software. You can't take a C, C++, or Python application and run it efficiently on a GPU. That is because GPUs are programmed using a domain-specific language like CUDA. This exposes the inner workings of a GPU. While potentially powerful, it requires developers to manage different memory hierarchy, cache coherency, and parallelism model. It took a decade for CUDA to get widespread user adoption. This shows how hard it was to shift software ecosystems. Resource trade-off. Another limitation has to do with computing precision and how hardware resources are used. Newer GPUs are optimized solely for AI workloads and not for HPC workloads. Think of precision like decimal places in math. HPC requires high-precision FP64 compute for accurate results for tasks like drug discoveries. AI can utilize a good enough lower precision FP4. This difference in precision means that there are major differences at the silicon level. For instance, you can fit 256 FP4 multipliers into the area of one FP64 multiplier, allowing for much more compute operations in FP4 using the same hardware footprint. It is easier to take an existing chip and show 256x better performance just by removing FP64, but it won't accomplish the same tasks. This lower precision optimization will cause bottlenecks for traditional HPC applications. Users who need high precision calculations are forced to compromise, paying for hardware that is not optimized for their needs. Power. Today's GPUs consume insane amounts of power, thousands of watts, with new data centers requiring over 1.21 gigawatt to power them, 10x more power than what they consumed only a few years ago. For CPUs and GPUs, performance and power consumption is interlinked. If you double the performance, but also double the power consumption, you haven't gained anything. What does this mean? GPU performance is misleading. Performance may seem to double with every generation, but this is not the full picture. When you normalize it for power consumption, GPU performance has actually plateaued. Most compute companies think they can solve these issues by building a better, faster GPU, and they focus on hardware challenges. At NextSilicon, we solve the challenges of CPU and GPU's architecture. We take a system-level approach. We offer a computing platform that provides 10x better performance, and it uses half of the power consumption for both HPC and AI. And guess what? It's a drop-in replacement. AI factories are here to stay. We are a plug-and-play solution capable to accelerate CPU code, AI, and CUDA. Our solution adapts instantly to future models. AI models are changing rapidly. Building a custom chip that accelerates today's model is futile. Designing and manufacturing a chip takes at least 3 years, risking becoming obsolete even before they launch. That's why we created a solution that is built for the future. I'm proud to introduce the first intelligence compute architecture. It's a complete reimagining on how hardware and software interact. Our architecture moves beyond the limitations of traditional approaches that force customers to rewrite software and adapt to the rigid hardware constraints. At the heart of our architecture is a smart software algorithm. It monitors the customer's application. It learns which portion of the code runs most frequently, and reconfigures our Maverick chip to accelerate exactly those parts. We make the hardware adapt to the software and not the other way around. So how does it all work? Our intelligent compute architecture is based on the Pareto principle, the 80-20 rule. And in massive parallel code, it's even more extreme. 1% of the code runs 99% of the time. Our sophisticated software algorithm understands what's happening in the application. ICA identifies those critical hot paths in real time. It reconfigures the chip to accelerate exactly those parts that matter now. It gives them more transistors, more compute, and more love at runtime. This asymmetric approach means we are not wasting silicon and power that rarely runs. Our approach is truly novel. It all started with a patent called runtime optimization for reconfigurable hardware. It's the core intellectual property that enables real-time silicon reconfiguration, something no one else has even attempted at this scale. Our technology transforms what was previously a static one-time compilation problem into a dynamic, continuously evolving optimization system. The result? A software-defined acceleration that will improve performance over time. We get 10x faster performance at half of the power consumption, and because we are a drop-in replacement, we can penetrate the market much more quickly. The Maverick ICA can deliver immediate performance with zero porting risk. We don't offer just a performance or efficiency improvement. We are offering a completely new way of how performance can be delivered. To conclude, we are building the chip of the future. A universal chip, better performance and greater efficiency. Our ultra-flexible design is engineered to be future-proof, delivering market-leading performance no matter how science and AI models evolve. And it does so as a true drop-in replacement. No rewrites, no vendor lock-in, no long, costly porting cycle. Just scalable performance ready for the future of humanity. Maverick isn't just built for the future, it's built to define it. Join us in shaping a new era of compute, where the possibilities are limitless. I would like to welcome on stage Eyal Nagar, my co-founder and EVP of Engineering at NextSilicon.
Hello everyone, I'm Eyal Nagar, co-founder and VP R&D at NextSilicon. It's an honor to stand here, not just to unveil our Maverick-2 product, but to introduce what we believe is a new era in compute. Throughout my career, I witnessed how Moore's law plateaued in real time. What was once a predictable cadence of performance became slower, more costly, and difficult to scale. It became clear that we could no longer depend on incremental hardware improvements. What the industry needed wasn't just better chips, it needed architectural innovation, a fundamentally new way to think about compute. That's why, when Elad Raz first shared the vision of NextSilicon with me, it resonated immediately. We aim to create a software-defined hardware architecture where the hardware adapts to the application and not the other way around. This vision is the foundation for what we believe is the future of compute: adaptive real-time performance optimizations. At NextSilicon, we took a bold mission to reinvent the foundation of computing. It's not just a slogan, it's a guiding principle that drives everything we do, from architecture to execution. To turn this vision into reality, we knew we had to own the entire stack, from high-level application all the way down to transistor. So we assembled a world-class team from across the globe, specialists in everything from compilers and runtime software to chip design and large-scale system production. What unites us is the relentless belief breaking the limits of traditional architecture demands a new paradigm. We love compute and we want it to be great. Our partners also share the same belief. We've worked with some of the most important technology leaders in the world, partners like Sandia National Labs, Los Alamos, Oak Ridge, HLRS, and many more. Today, I'm proud to introduce Maverick-2, our next-generation compute accelerator, which is already running at customer sites and showing remarkable performance. Using its intelligent compute architecture, Maverick-2 delivers performance, efficiency, and scalability as it plugs directly into your system. Maverick comes in a PCIe card, full-height, double-width form factor, and it's powered by our massively parallel data flow grid. We also offer an OEM form factor version designed for efficient compute at scale for higher density. This isn't just a chip, it's a complete reimagining of how hardware behaves. Let's start with the single die version. It's built on TSMC 5nm process. It runs at 1.5 GHz and supports PCIe Gen 5x16 for maximum host connectivity. On chip, it features 96 GB of HBM3 memory, delivering a massive bandwidth of 3.2 TB per second. Maverick features a remarkable 128 MB of L1 cache system designed specifically for HPC and AI workloads. Smart, on-chip, and optimized for sustained throughput. Now, your most demanding workloads will stay close to the compute engines where they can run at top speed. We also included a 100 gigabit Ethernet link for node-to-node interconnect. The TDP for this card is 400 watts, and we offer both air and liquid cooling options for flexible deployment. Now let's scale it up to our dual die. This version uses an OCP accelerator module or OEM form factor. And as you can see, the data flow performance doubles along with everything else. HBM memory is as high as 192 gigabytes, with enormous bandwidth of 6.4 terabytes per second. The TDP also doubles up to 750 watts. In real applications, we're seeing utilization that's lower than that, so performance per watt is exceptional. You might be wondering why we use HBM. High bandwidth memory is critical for HPC and AI. It provides enormous data throughput directly next to the compute engines, reducing latency, power, and bottlenecks, which slows down the application. For Maverick-2, we chose the best HBM technology available on the market, because for our customers, memory bandwidth is just as important as raw compute power. We didn't stop at the chip. The entire interconnect system is built for scale. This is critical for scaling performance across nodes in large HPC systems. And with our partnership with companies such as Penguin, Dell Technologies, and more, we made sure Maverick-2 integrates seamlessly into standard infrastructure, so you can deploy tomorrow's performance using today's racks. Now, let's talk about what truly sets Maverick apart. Not just the hardware, but the intelligence behind it. Traditionally, to accelerate your code, you had to do the heavy lifting yourself. You'll spend days, weeks, and sometimes months manually picking which parts to offload, rewriting them for specialized hardware, and hoping it all works seamlessly. This is the porting barrier that has plagued our industry for decades. We all lived through the difficult transition of moving applications from CPUs to GPUs. This process demanded specialized skills and vendor-specific programming languages. We engineered Maverick to be a true drop-in replacement. Our goal is to let your application run without major code rewrites, while keeping it fully portable. Maverick's smart software does the work for you, watching and learning in real time. It identifies the most computationally intensive parts of your code, the hotspots, and automatically targets them for acceleration. No guesswork, no manual tuning. Once a hotspot is detected, Maverick-2 optimizes that specific piece of code and applies an automatic configuration of the data flow grid to act like a custom-built, ultra-efficient microfactory engineered for that task. And it all happens under the hood. When your application calls one of these functions, Maverick's software intercepts the call and redirects it to the chip. From your application perspective, nothing has changed. But under the surface, performance just skyrocketed. And the more you run, the smarter it gets. Maverick-2 collects telemetry as your workload runs and uses it to continuously refine and re-optimize how tasks are mapped to the hardware. In other words, Maverick doesn't just run fast, it gets faster the longer it runs. This is what we mean by intelligent compute. It's a system built for adaptive, real-time performance optimization. Instead of a fixed function accelerator, our software-defined hardware dynamically learns from your workload and reconfigures itself in real time. A system that adapts, evolves, and maximizes performance, not just once, but over and over again, automatically. That's not just innovation, that's transformation. Maverick's data flow presents another breakthrough innovation as it delivers two dimensions of parallelism. The first is massive threading, which allows the grid to handle many parts of a task simultaneously. Imagine a large team of workers all doing different parts of a big project at the same time. And the second is a deep data vectorization, which gives the ability to process multiple pieces of data with a single operation. Our powerful data flow grid excels at massive parallel execution, and we use our intelligent software to run it at maximum efficiency. Our customers can run their existing code in any language on our chip and instantly unlock higher performance. Using these innovations, Maverick-2 brings NextSilicon's vision to life by introducing hardware designed to be incredibly efficient and eliminate common bottlenecks found in traditional CPUs. There are no instructions, No out-of-order logic, no branch prediction, no wasted die area. Our intelligent compute architecture avoids them, leading to a much higher power and performance efficiency. The landscape of HPC and AI is in constant flux. Today's cutting-edge algorithm quickly becomes tomorrow's legacy code. To keep up, your platform must do the same, delivering efficient performance not just today, but tomorrow as well. Our industry needs next-generation compute to have a future-proof design. This is our final architecture breakthrough. Because Maverick's software-defined hardware adapts to the code it is given, it isn't locked to any single type of algorithm. Whether you are supporting today's transformer models or next innovation in AI, our architecture is designed to learn and accelerate that new workload. This ensures your investment remains robust and relevant for the years to come. What we've discussed in detail today is more than a chip, it's a foundation, a new way to think about compute. It opens a whole new world of possibilities and optimizations for engineers and scientists. We want to empower you to provide more value than you ever thought possible. Maverick-1 validated the fundamentals of our technology and proved our core concepts work. Maverick-2, our flagship product, is a revolutionary chip that has already been chosen to power the next generation of computing at Sandia National Labs as part of the Vanguard 2 supercomputer. We have only just begun to fully optimize the hardware and software stack, and we are already delivering breakthrough performance that surpasses existing solutions. I eagerly wait to see what innovations our team and partners unlock in the years ahead. And I couldn't be more proud of the incredible team that made it all real. Thank you.
I would like to welcome on stage Ilan Tayari, my co-founder and VP Architecture at NextSilicon.
Hello everyone, my name is Ilan Tayari. I'm the VP of Architecture and a co-founder at NextSilicon. In my 30 years of work, software and hardware architecture have been a central part of my life. Over the years, I developed the ambition to revolutionize the way we design chips and systems for performance. Founding NextSilicon allowed me to realize this vision. This sounds a little abstract. Let me show you what this means in practice. Computing platforms shift every 10 to 15 years. Each transition unlocks new categories of problems that humanity can solve. Mainframes to PCs, client-server to cloud, CPU to GPU. Each transition made previously impossible applications turn into something routine. But here's the thing. Each transition happened because the previous platform hit fundamental limits on the problems it could solve. The next transition will allow scientists to reach beyond what is possible today. Imagine biologists researching cancer using molecular simulations across thousands of human cells. Picture astronomers exploring dark matter with unprecedented granularity across galaxies to uncover fundamental properties of the universe. Consider accurately forecasting natural disasters like floods, hurricanes, and forest fires early enough to save thousands of lives. Innovations in physics, finance, energy production, sociology, the list goes on. All of these discoveries shape our future. Our vision to liberate us from the confines of computation has never been more critical than it is now. Today's research in all fields of science is inherently parallel. Scientists rely on parallel computations to fuel their breakthroughs in all fields of science and technology. But there's the problem. Today's GPUs and CPUs struggle to perfectly execute parallel applications at scale due to their inherent design characteristics. These traditional designs of instruction set processors are based on the von Neumann architecture, first introduced over 8 decades ago in the 1940s. The design principles include a single unified memory space that holds both program instructions and data, an instruction fetch unit, which reads instructions from memory according to a program counter, an execution unit, which executes compute and memory access instructions using general-purpose registers, an ALU that performs computations, and an MMU, which translates memory addresses. While brilliant for its time, this design created some critical problems. First, the use of a shared memory bus causes a bottleneck. This is the communication pathway connecting the processor to system memory. It must handle 3 different mechanisms simultaneously: the instruction stream, memory management, also known as page walks, and the actual data. Second, the instruction set processor is serial and therefore very sensitive to latency. Memory accesses can have long latencies. Whenever an instruction accesses memory, the ALUs are stalled, waiting for the data to arrive. Here's the scale of the problem. From 1980 to 2025, frequencies grew 1,000 times, but DRAM latency, it improved just by 5 times. As a result, modern processors spend most of their time waiting for data rather than processing it. To reduce stall-inducing latency, early processors introduced multiple caches. Caches are small, fast memory units near the processor. They store recently used data, so the processor can access it again quickly instead of going to main memory. Instruction caches were introduced to reduce instructions fetch latency. Translation look-aside buffers were introduced to avoid costly memory management operations. Data caches were added to speed up data memory access. But caches are not enough. Modern processors try to do everything as early as possible, using many advanced techniques. They look ahead and prefetch future instructions into the cache, hundreds at a time. When instructions contain branches for decision points, the processor fetches multiple instruction streams, sometimes dozens of different paths. This in turn uses more memory bandwidth, so the processor applies branch prediction heuristics, essentially guessing which branches are worth prefetching and which aren't. It executes some instructions out of order, some before they're actually needed, sometimes even while other instructions are accessing memory. The mechanism that identifies when and which instructions can execute is a sophisticated out-of-order engine. It even attempts to access memory and perform computations speculatively. That means executing operations before knowing if they are actually needed. These solutions can increase performance, but they also have high costs. They take a lot of silicon real estate, and the mechanism to revert missed predictions has a large negative impact on performance. Here's the shocking reality. Today's high-end processors have become complicated and chunky, both physically and practically. They dedicate 98% of their silicon to overhead, traffic management, data shuffling, not actual computation. Add any more complexity, clock speeds suffer, and slower clocks means slower execution. Some GPUs devote up to 30% of their silicon to compute. But because the blocks are mutually exclusive, only a few can run at once. All of these efforts to improve processor design are merely reactive solutions, workarounds. End users pay 3 penalties. The chip costs more, power consumption increases, cooling requirements grow. Everything becomes more expensive. We're stuck in a costly trade-off, and that's exactly where NextSilicon comes in. Instead of trying to patch this 80-year-old model with sophisticated workarounds, we needed to embrace a new one. What if we could dedicate the majority of the area to ALUs, the units that actually perform computations? A chip like that would have the potential to get 10 times the performance at a quarter of the power consumption. That brings us to a dataflow architecture. In direct contrast to von Neumann, dataflow is a data-driven paradigm, where the data drives the program and the optimizations on the hardware, not the other way around. The main unit is a compute block, made almost exclusively of hundreds of interconnected ALUs. Each ALU is analogous to a compute instruction. Each ALU is configured to perform a specific operation: addition, multiplication, bitwise logic, bit shifting, and so on. The main unit is attached to a memory bus to receive data. When the data arrives, it is temporarily stored in a reservation station. A dispatch unit determines when it's time to trigger the compute block. This combination of a reservation station, dispatcher, and dataflow compute block is a NextSilicon unique and patented innovation. The RS and dispatcher are analogous to the general-purpose registers of an instruction set processor. The main unit also contains memory entry points, MEP for short. These handle memory access operations, similar to memory instructions in a traditional processor. Here's how MEPs work. The MEP takes a computed address and data to read or write. It generates a memory access request on the memory bus, then directs its completion response to a reservation station. That's the part of the processor that is waiting for the result. And since the address may be virtual and require translation, the unit uses both an MMU and a TLB cache. This MMU serves only those memory access operations of the local unit, so its cache is very effective. Think of it as a private MMU for specific memory access instructions in your program. NextSilicon's dataflow architecture allows us to achieve significantly lower overhead compared to traditional CPUs and GPUs. We pivot the silicon allocation ratio. We dedicate the majority of the resources to actual computation, rather than control overhead. Our approach uniquely eliminates instruction handling overhead. We minimize unnecessary data movement. The result? Compute units stay fully utilized. We're not trying to hide latency, but to tolerate and minimize it by design. Let's go one step further and see how compute programs map to this. To understand how a function runs on the dataflow architecture, let's look at the code sample of a reverse function. This is a bit reverse function for 32-bit integer. The compiler builds an intermediate representation graph for it. A CPU compiler takes this graph, turns it into registers and instructions, and then encodes them into machine code. Compiling to a dataflow processor is different and a little simpler. The compiler maps each graph operation to a hardware element, an ALU, in a process called projection. The graph is projected onto the dataflow processing grid. No more register assignment, no more instruction scheduling. Instead, the compiler generates configurations for hardware elements and their dataflow, similar to machine code. The resulting entity is what we call a mill core. It is a software-defined hardware. An application-specific processing core optimized for a particular application. We named it after Charles Babbage's mechanical computer and the traditional sense of a mill. Unlike a CPU core, the mill core is software-defined, and it only consumes the resources it requires. For example, one mill core might be very compact, taking only a portion of a compute block, while another mill core might be more complex, spanning multiple blocks. One of the mill core's key dimensions is its logical height, which affects latency. As you can see, an instruction set processor goes to great lengths to minimize latency, both for individual instructions and for the overall computation. The result of both types of processors is similar. In this example, both the CPU and the dataflow processor execute this function in about 14 cycles. Traditional processors invest most of their silicon in control complexity, traffic management and scheduling systems, all to improve the utilization of the small fraction dedicated to actual computation, namely the ALUs. But this approach resulted in shrinking the relative area dedicated to ALUs to roughly 2% of modern-day CPUs. In contrast, dataflow designs invest the majority of the silicon real estate in compute. This change alone dramatically increases the chip's potential. When you have more compute silicon to utilize, you get much higher performance. Up until 20 years ago, most effort was put into making processors faster by improving transistor density and efficiency. But this method reached diminishing returns, so designs now scale differently. One method is adding multiple cores to a chip, essentially multiplying the processor. This brings the challenge of keeping cores coherent, for example, ensuring their data caches stay in sync. So these designs add a cache coherence mechanism, which snoops other cores and invalidates stale data. And then, to scale cache capacity, these designs add shared Layer 2 and Layer 3 data caches to groups of cores. In a dataflow processor design, things are much simpler. In a dataflow processor, the same software-defined mill core configuration is replicated side by side, naturally scaling concurrency. We only duplicate what's needed. Smaller mill cores can be replicated more times. This maximizes utilization across the entire dataflow grid, no matter how complex your application. And here's another bonus. The dataflow processor switches between different kernels of the application extremely quickly and reconfigures itself on the fly in a matter of nanoseconds. As your application changes, so does our hardware setup. This is called mill scheduling. Another way to scale is superscalar processing, when a CPU executes instructions out of order. This means it can sometimes execute multiple instructions concurrently, using more than one ALU or memory access unit. Sounds good, right? But it comes at a cost. Superscalar processors require massive overhead, complex register renaming and management, sophisticated execution coordination systems, all this overhead just to figure out which operations can run independently. All just to achieve some parallelism. Modern CPU designs also employ vector instructions. These vector instructions access multiple memory elements at once, then apply the same operation to multiple values simultaneously. In traditional processors, this technique requires special hardware, dedicated vector registers, and vectorized ALUs. In a dataflow processor, the superscalability and vectorization are built into the design, reducing redundant operations. ALU interconnections allow multiple units in a row to execute concurrently, performing several operations at once. By projecting wide compute graphs, we save power and dedicate more resources to actual computation. In a similar fashion, we get vectorization for free. It's just how it works. The memory unit loads multiple data points at once, then ALUs in the same row each take a different piece of the data. Each is configured to perform the same operation, but on different data elements of the vector. Traditional CPUs and GPUs also use multiprocessing. In GPUs, it's called streaming multiprocessor. One instruction stream is fed into multiple execution units. They all operate in rigid lockstep, perfectly synchronized. This synchronized group is called a warp or a wavefront. In CPUs, it's the simultaneous multithreading. Execution units work independently of each other, but they share the front-end caches and blocks. You might know this as hyperthreading. In both cases, multiple threads run concurrently on the same core. Each thread maintains its own state and data. And just like before, these mechanisms incur additional silicon and power overheads, making the core much more complex, just to allow a bit more parallelism. Our dataflow processor works differently. CPUs are latency machines. They execute one task quickly. Dataflow processors are throughput machines. They execute many tasks simultaneously. Imagine one thread executing on the dataflow mill core. At any point in time, or rather at any clock cycle, you may find it at any one of the 14 rows crunching its data. By the next clock cycle, it would progress one row, gradually advancing through the graph logic. So a single thread is not utilizing the mill core much. A given ALU only works once every 14 cycles. But now imagine another thread, executing right behind it on the previous row. At any point in time, you may find both threads next to each other progressing through the graph. And now imagine that we have enough threads to cover the whole mill core top to bottom. With this number of threads, the mill core is fully utilized all the time. At any point in time, all rows are occupied by threads ready to execute. That means that every ALU is working and crunching data at every clock cycle. This is where data flow becomes extremely efficient. Traditional processors excel at single-thread performance. Our dataflow processor excels at massive parallelism, running 14 threads simultaneously in this example, one per row in the compute graph. Both are designed to have the same latency, but the dataflow processor gets much higher throughput. One result per cycle, regardless of the computation complexity. This is a key strength of our design. Let's put this in perspective. Traditional CPU cores handle 2 threads simultaneously. GPU cores handle 32 or 64 threads. Our mill cores can accommodate hundreds of threads at once. That's the power of moving beyond the 80-year-old von Neumann architecture. The dataflow approach works amazingly well for AI use cases. Modern AI models are built from two types of operations: matrix multiplications and pointwise vector operations. AI chips and GPUs use specialized circuits for these, namely tensor cores and vector units. Data constantly gets pushed in and out of these units. We just do dataflow. The same dataflow processor runs both types of operations out of the box. Let's look at an example from AI. This is the sigmoid linear unit, or SILU, activation function. A simple implementation of SILU looks something like this. This activation function is always applied pointwise to a vector of numbers. So when compiling the mill core on a dataflow processor, the compiler generates a vectorized graph. Here's how vectorization works. Instead of loading one element at a time, we load many at once. Then we apply the same calculations to all of them simultaneously. It's like vectorized compute instructions. In this case, it may result in a vectorized load and store of 16 elements. So the computation may be repeated up to 16 times and fit in a single compute block. This mill is then replicated across the dataflow grid, so when the activation function is executed, thousands of elements may be processed concurrently. So the overall runtime of this MLOp becomes very, very short. Then a moment later, the dataflow grid is configured to perform matrix multiplication, to continue execution of the AI model. No special programming languages required, no code rewrites. It works with your existing code and AI frameworks. And it's not limited to what exists today. For AI researchers, this method opens up new exciting options. You get acceleration no matter what your model uses. Exotic activation functions, complex numbers, or novel mathematical operations. Everything is accelerated out of the box. We don't use specialized hardware for specific MLOps, so our technology is truly future-proof. Of course, hardware is only half the story. The best hardware in the world is useless if you can't program it. Historically, this has killed the adoption of dataflow architectures because it required users to write applications using domain-specific languages. But we've solved it. You don't need to learn a new language or rewrite your code, whether you're working on C++, Fortran, Python, CUDA, ROCm, OneAPI, or even AI frameworks. Our architecture is language and framework agnostic by design. During compilation, your code is transformed into a fat binary with two parts. One part is native for the host CPU, and the other is intermediate representation. At runtime, our system takes over. It identifies the hotspots and the potential bottlenecks in your most likely code paths, all from the intermediate representation. It creates the mills and projects them onto the Maverick dataflow grid. The rest of the code continues running seamlessly on the host CPU. But we don't stop there. This is where the intelligent part of our architecture truly shines. Maverick uses live telemetry to constantly optimize the application. This is what we call runtime optimization. For example, if two mills communicate frequently, they will physically relocate closer together on the chip to reduce latency. If there is a bottleneck, the mill duplicates to increase throughput. These optimizations happen dynamically with zero developer input. This is more than just optimization, it's evolution at the speed of runtime. And because our system is also AI stack agnostic, it works across the full range of modern machine learning tools and frameworks, from TensorFlow, JAX, PyTorch, or Onyx, and anything you'll find on Hugging Face, including specialized custom MLOps written in CUDA or Triton. You don't need to modify your application to get acceleration. Our architecture learns your workload and adapts to it, not the other way around. Remember CNN-specific accelerators? They're paperweights now, useless for today's transformers. This is the ASIC trap. optimized for today's models become obsolete tomorrow. With Maverick technology, we're utilizing general-purpose silicon to do AI computation. No matter what the next generation of AI models look like, whether it's some exotic activation function, MLOps, or something we can't even imagine today, our technology is future-proof, and we'll be able to accelerate it without any added cost. So, where are we headed? The von Neumann problems aren't just technical barriers. They're holding back human progress. We're not just breaking through that wall, we're building a bridge to the future. When you eliminate technical barriers, when computational limits stop holding back imagination, that's when we truly accelerate human knowledge. That's when innovation happens. The future of computing isn't just faster, it's fundamentally different. And to clarify, reconfiguring silicon on the fly at nanosecond speed is incredibly hard. It's complex, it's groundbreaking. And it's precisely why no one else has succeeded or even attempted this before. And guess what? Not only did we tackle this challenge, but we made it work. At NextSilicon, we're rethinking compute at its very core, making the hardware adapt to your software, not the other way around. Just as GPUs once displaced CPUs, our architecture is poised to redefine compute all over again, and it's right around the corner. I invite you to use it to shape your future too. Thank you.
We have spent the past 7 years building a chip of the future, and now we have the opportunity to reveal our results. Let me show you how Maverick-2 delivers on our promises. Today's most demanding applications, such as agentic AI, graph analytics, and scientific simulations, aren't limited by compute. They are strangled by memory access. Our competitors are focused on adding more cores, more teraflops, more theoretical performance, but they ignore the real bottleneck that has been staring at them for a while. How fast can you actually reach your data? This limited every architecture before us, and it's exactly how our ICA stands apart. Let me show you how Maverick-2 redefines acceleration. When you build a new chip, the first test everyone runs is Stream. Whether it's a CPU, GPU, or a new architecture, Stream is the industry standard starting point. And companies invest a lot to tune Stream for their systems. Why? Because Stream tells you how fast your system can move data. It tests the memory fabric, or how efficiently your chip can transfer large amounts of data between the processor and the memory. Think of it as checking the speed and width of your system's data highways. Teams spend hours, even days, fine-tuning their systems just to squeeze out more performance from Stream. For us, full scaling of our HBM, right out of the box. No tuning, no custom optimization. This isn't just a benchmark victory. This gives developers confidence, performance that translates directly to the real applications. No surprises, no disappointments, just faster results from day one. Stream proved our memory subsystem delivers. Now let's stress it with real chaos. Gaps is where most architectures have failed, and it's where our ICA stands out. Let me tell you what gaps is, and why it broke every existing architecture. Gaps is messy, it is unpredictable, it stresses a system with random memory access patterns. That randomness is exactly what makes it so challenging. Gaps test the entire memory fabric. This includes latency, bandwidth, I/O contentions, and cache behavior. Today's most demanding workloads like agentic AI, graph analytics, and scientific simulation are limited not by compute processing power, they are limited by memory access. A high gap score shows that a platform can handle complex, memory-intensive workloads. On the left, you can see the original CPU code. On the right, you can see how it runs on GPUs. Heavily modified code, almost unrecognized. Now let's see how GPUs outperform CPUs in performance. See how much they are faster? We run the original CPU code, unmodified, and deliver even better performance. Maverick-2 delivers 32.6 GOPS at just 460 watts of total power consumption. Here is the remarkable part. Our team achieved this using completely unmodified code, out-of-the-box code. No specialized team needed, no months of optimization required, no vendor-specific code changes locking you in, just plug-and-play breakthrough performance. And this is just our starting point. Our team has a clear line of sight to deliver ongoing improvement through software optimization alone. Another one of the many benefits of the ICA architecture. Moving to more complex workloads. HPCG is the gold standard benchmark for HPC. Win HPCG and you won science. HPCG is designed to reflect real-world HPC workloads. It tests memory access, communication, and computation balance, the combination that matters the most. Traditional CPU and GPU architecture often struggle with HPCG. CPUs are flexible but lack throughput. GPUs are fast for regular tasks but suffer performance drop on HPCG workloads. Why? Inefficient memory handling and poor adaptability to sparse operation. NextSilicon's adaptive architecture is built for this challenge. We dynamically optimize for memory access patterns and workload structure. We maintain high performance even under HPCG's demanding conditions. Bottom line, strong HPCG performance means faster time to scientific breakthrough. Maverick-2 delivers 600 gigaflops at 750 watts. Out of the box, we are beating the performance of the most widely deployed GPUs in the industry, at half the power with zero code changes. Let me repeat that. Better performance, half the power, zero code changes. Our software-defined approach dynamically optimizes for these demanding access patterns in real time. This architecture doesn't just handle HPCG's complexity, it shines on it. And this is just our starting point. These results are just at the device level. Imagine the potential when scaled to many devices at the system, rack, and data center level. You won't have to wait long. More details on our performance at scale coming soon, to be announced with our customer, Sandia National Laboratory. Stay tuned. Now, let's look at graph analytics. Using PageRank, the algorithm that started at Google to rank billions of pages. Now it powers everything, from social media to AI reasoning. These graph applications use sparse patterns, irregular memory access patterns. Traditional architectures cannot handle them efficiently, and at large scale and sizes, cannot process them at all. Maverick-2, 40 giga pages per second, a whopping 10x performance over leading GPUs at half the power. But here is what's even more remarkable. When we tested large graph sizes, particularly beyond 25 gigabytes, GPUs began to struggle. Some couldn't process the graphs at all. They simply failed to complete. Maverick-2, it handled them effortlessly. No failures, no crashes, no compromises. And here is the real game changer, with up to 192 gigabytes of memory. That means we have even more room to scale. Multiples of these large 25 gigabyte plus graphs running simultaneously, or individual graphs that dwarf GPU capabilities. This isn't just about better performance. This is about unlocking possibilities that GPUs simply cannot deliver. Here is the truly transformational part. Every single result I just showed you, achieved using existing, unmodified application code. Our competitors require specialized teams to modify code, BIOS, firmware, operating system, parameters, just to hit their published benchmarks. NextSilicon delivers superior results using the software you are already running. This is the promise kept of a true drop-in replacement. Bring your own code, keep your existing processes, get breakthrough performance, no vendor lock-in, no lengthy porting cycle, no risk. And remember, these are our starting point numbers. Our team has a clear line of sight, expected improvements across every benchmark through software optimization alone. That is the power of a truly software-defined architecture. These aren't just impressive numbers. They are proof points of immediate advantages. For the computational challenges that matter most, for HPC researchers, faster time to scientific breakthroughs using the applications you are already running. For data center operators, half the power consumption, operational savings and scaling beyond current power constraints. For everyone, future-proof investment protection. As algorithms evolve and application change, Maverick-2 adapts automatically. 7 years ago, our team envisioned a different path. Not just faster chips, but smarter architecture. Not just more performance, but more efficient performance. Not just breakthrough numbers, but breakthrough value. Today, you have seen that vision become reality. Across gaps, HPCG, Stream, PageRank, and more, breakthrough numbers at a fraction of the power, delivered through software-defined intelligence that adapts to your applications, not the other way around. The future of computing isn't just faster, it's smarter, it's more efficient. It's here. Maverick is here, and we are just getting started. I want to show you one more thing. This is the Maverick-2. And today, I'm proud to introduce Maverick's little test brother, the Arbel. When we started NextSilicon, we didn't just want to build another accelerator. We wanted to prove what true innovation looks like in the industry. We set out to create an architecture that evolves with the algorithms. A system flexible enough to handle whatever comes next. That's exactly what we built with the ICA. But here is what we learned building ICA and Maverick-2. Every application has two fundamental parts. There is massive parallel code that our dataflow grid handles, and there is serial code that needs to execute with low latency in a CPU core. So we build our own RISC-V cores right into the Maverick-2. Our RISC-V handles the less likely code of your application and serial code. And you know what? Those cores performed so well that we started thinking, what could be possible if we test it with a dedicated chip? The result is what you are about to see. Here is the Arbel, a new enterprise-grade RISC-V performance core. We built it from the ground up. Arbel delivers breakthrough performance through 4 key innovations. First, we have built a massive instruction pipeline. It has a 10 wide issue width with a 480 entries in the reorder buffer. This means we can see more of the problem at once. Second, we build a wide execution unit that supports 16 scalar instructions in parallel, 6 ALUs, 3 load address calculation units, 2 store addresses calculation units, 2 store dispatchers, and 3 branch units. We have 4 128-bit vector units. This provides a core with an exceptional performance. Third, we have built a sophisticated memory subsystem, 64 kilobyte L1 cache and a large shared L3 cache. Finally, our Tage branch predictor ensures we are making the right decisions. Fewer wrong guesses and less wasted time. And we cache only the taken branches. These 4 pillars provide a massive leap in RISC-V performance delivered by NextSilicon. This isn't academic research. This isn't a roadmap slide. This is silicon, real, physical, built on TSMC 5nm process, every transistor, every pipeline stage, all designed for speed and to accelerate our customers' most demanding workloads. This is our own patent IP, not licensed, not borrowed, built by NextSilicon engineers for NextSilicon vision of the future. Here is something I can tell you. We are crushing the current RISC-V competition, and we are standing toe-to-toe with Intel LionCove and AMD Zen 5. This is not a catch-up core. This is a leap ahead core. Now, you might be thinking, is NextSilicon becoming a CPU company? Not exactly. But we are exploring something much more interesting. We are seeing tremendous customer interest in Arbel. It opened our eyes to the same opportunity that AMD and NVIDIA have recognized, the power of vertical integration between CPU and accelerator technologies. When you control both the general purpose computing and the specialized acceleration, you can optimize the entire stack in ways that simply aren't possible. This demonstrates NextSilicon's fundamental capability to innovate at the deepest levels of computing architecture. Our customers aren't just buying a product, they are partnering with a company capable of building best-in-class accelerator processors, one that can solve problems others can't. So that is our one more thing for today. Not just the industry's most advanced dataflow accelerator, not just another RISC-V announcement, but proof that NextSilicon doesn't just talk about innovation. We built it from the ground up, in silicon. While others share their plans, we are sharing our results. Thank you for joining us today, and stay tuned. We are just getting started.